Welcome to the notes for 10.8. We're going to be graphing polar equations. A polar equation, we talked yesterday about graphing in the polar coordinate system. A polar equation is just an equation that involves r's and theta. So your coordinates are r's and thetas rather than x's and y's. I'm going to split these notes up a little bit. We're going to focus on the different types of graphs. There's circles and cardioids and roses. Those are our primary focuses. And so I'll break them up just so that the note set isn't quite so long. Before you get started, you're going to want to pause and grab yourself a graphing calculator and or a scientific calculator. Just know that on the test, I would not give you a grapher, but it is helpful sometimes just to see what your answer should look like. And then on the test itself, you'll be able to use a scientific. So we're going to start with just the most basic method for graphing any equation. In fact, it's probably how you started graphing rectangular equations back in middle school. We're going to start by plotting points. For a polar equation, you want to pick the theta and then compute your r. So for example, if my equation is r equal to 4 sine theta, then I can pick some of my favorite values from the unit circle and I can start plugging them in. Now some of them will be easy. I can plug in 0. The sine of 0 is 0. So 4 times 0 would be 0. And pi over 6, the sine of pi over 6 is a half. 4 times a half is 2. And then I'll quickly move into some territory where I could probably come up with the values, but graphing something like a root 3 isn't going to be very easy to do given my grid paper here. So I would suggest that you use a calculator to just compute some of these values. So I'm going to grab my grapher just to have it handy here, and I would type in 4 times the sine of pi over 3. Double check that you are in radians. You should be in radians for everything that we're doing here. And I get about 3.5. Now, realistically, I should write down a few more decimal places, but 3.46 in my table will be fine. I'm not going to be able to graph very accurately. If I plug in pi over 2, sine of pi over 2 is 1. I get a 4. And I could keep going this way and plugging things into my calculator, right? 4 times the sine of 2 pi over 3. I'm going to get 3.46 again. 2 here, and just I'm going to fill these in really quickly. We could do a lot more coordinates if we wanted to, but I happen to know how this one graphs, and I don't need quite as many points to get there. So I've effectively plugged all my thetas into my equation, and I've gotten the r's that go with them. So here's what we want to do. We want to backtrack to yesterday's work and start plotting these points. Remember, theta gives me my direction. R tells me how far to move in that direction. So in the direction of a 0 radian angle, I want to go 0 units. That would put me at the pole. In the direction of pi over 6, I would want to move 2 units. So I'm going to use those little circles to go 1, 2 units in the direction of pi over 6. I didn't put pi over 4 in here, but if we wanted to, we could add that one in, right? It was 4 times the sine of pi over 4, so around 2.8. So let's see, a little less than 3 when I'm at pi over 4. Excuse me. At pi over 3, right, I'm going to go out about 3.5. The grid paper is not perfect here. At pi over 2, so in the direction of pi over 2, I'm moving up 4 units. And in the direction of 2 pi over 3, I want to stay about the same as I was over there, 3.46. At 5 pi over 6, I'm out 2 units. And at pi, I'm back to 0 again. So let's connect the dots and sort of see where we're at so far. Remember, I would also be plugging in all these other angles between 0 and pi over 6. And kind of like parametric, I want to follow sort of the pattern of how I plugged them in when I'm connecting my dots. And this particular graph would graph as a circle. Right? If I go to 7 pi over 6, right, that would be right here. But my negative radius would actually send me in the direction of positive pi over 6. And so I would go 2 units, and I would land right on top of where I was already at. And so that's why I stopped picking points, because if you continue this pattern, you end up just graphing right on top of where you already were. For example, at 3 pi over 2, I'm going -4 for my radius, so I'm actually going towards pi over 2, and I'm just overlapping. So just like the unit circle, it would just keep graphing on top of itself. It's a little hard to tell here. It's not a perfect graph, but this is actually the graph of a circle. Unlike yesterday, it's centered at 0, 2, and it has a radius of 2 units. In fact, in general, anytime I have an equation that looks something like this one, I will always get a circle. So notice here, if r is equal to a, so a can be any value, it could be 2 or 4 or 3, it could be a fraction, doesn't really matter, and then times my trig function. So if you have an a times a cosine or a sine theta, you will always get the graph of a circle. So then if you were in class today, I would have asked you to grab that graphing calculator and just really quickly take a moment on your graphing calculator to sketch, and I don't need as much detail here, just a quick sketch of what this would look like. Before you do that, I should probably show you how to graph in Polar. So let me move out of the glare here. Just like we had changed our mode right next to the blue button, I'm going to press mode. Remember, we've always been graphing up until this past week. We've been graphing in function territory. This is your rectangular coordinates, your x's and y's. We just finished talking about parametric, and now if I move over to POL for polar, I'm going to press enter to select it. And then when I press y equals, notice there's no more y's, there's no x's and y's with sub t's for parametric. Now I have r values. And when I press the x coordinates, it'll pull up a theta because I'm in polar coordinates. One note, again, make sure that your mode is in radians or this will not work right. So you want to go back to y equals. And for example, let me just show you what I mean by a quick sketch. Let's type in the next one, 4 cosine of theta, close it out, and I'm going to look at my graph. Okay, you can kind of use the tick marks here, 1, 2, 3, 4, right? And I'm just going to quickly sketch that it went out 4 units, and it's in that what would have been the x direction previously. Now we're on the polar axis. So go ahead, pause the video, type in these others, and make me a quick sketch. I'm going to assume that you've done that now and you come back, so I'm going to sketch mine in really quickly. And hopefully you noticed that this one was a little bit smaller. In fact, it ended at -2, but it was a cosine function. It is still hanging out on the x-axis. The third one, right, you're again a little bit smaller. 2 sine theta looks something like this. And a -3 sine theta, this one was a little bit bigger. It went all the way out to -3. This one was out to +2. And I put here, can you describe a quick way to connect the equation of to the location of the circle? So once you have memorized that this is the formatting for a circle, you can actually graph these a whole lot faster than what we did up here. Right? What do you notice? It goes out 4, it goes out 2, it goes out 2. That a value is your diameter. You can see that in the one that we did at the top. And then the other thing that I noticed is that when I have a cosine function, my circle is cut in half, right? It's symmetric about the polar axis, or what used to be the x. And remember, when we talked about cosine, when we first defined our trig, cosine was always associated with x values, sine was always associated with y's. And every time I'm graphing one of these circles with a sine function, then my axis of symmetry is what corresponds to the y-axis. So I just made a quick note here that a positive cosine function is going to put your circle on the x-axis. Oops, I should say positive x-axis. And a negative cosine centers it on the negative x-axis. And then likewise, a negative or a positive sine function here is going to place your circle on the positive y-axis. And a negative sine function puts your circle on the negative half of the y-axis. So in reality, when I'm graphing these polar equations, I usually use sort of a mix. I memorize some of these special forms. If I can identify this as a circle, I can graph it very, very quickly, and I don't need to make a giant table of values. If I forget what it's going to look like, I can always fall back on plugging in values into my calculator and plotting points. And when we get into some of the harder ones, we'll do a little bit of both. We'll sort of know what we're going to expect, and we'll plot points to fill in some of the details. The last part on this page is just this test for symmetry. Notice that when I have a function that is a function of sine, right, then my axis of symmetry is the line theta equals pi over 2. It's what used to be our y-axis. If I have a function in polar that is a function of cosine, then I will have symmetry with respect to the polar axis, which is essentially theta equals 0, or your x-axis previously. And we're going to talk about this when we move into the next grouping. So I'm going to pause here, and we're going to come back and we're going to talk about something called cardioids.